Let's wrap up the last bit of conversions, the delta to y and y to delta conversion. The objectives here would be to perform conversions both ways, delta to y, y to delta, and apply delta to y conversion then to a bridge circuit, where you'll see that has its greatest applicability. So as we showed before, if we had relationships, and you've seen these in some of the example problems and the quiz that I gave you, you've got a delta here with 3 resistors, and with the right math, you can convert that to the y with the 3 resistors on the right. So if we overlay one on the other, this is the quickest way to remember how the transformations or the conversions occur, because what happens is between RA and RC, we're going to get a value for R1. Between RC and RB, we're going to get a value for R2. And between RA and RB, we're going to get a value for resistor 3. Okay, so we're going to do a conversion here as an example. It's right out of your text. Convert the delta network to a Y network where we got 3 resistors, 100 ohm, 220 ohm, and 560 ohm. So if you take a look in your text, you'll see that there are 3 canned relationships that allow you to solve for R1, R2, and R3. So in the case, as I said, of R1, you're going to use RA and RC plus the sum of the 3 to determine that the conversion is a 25 ohm resistor. For R2, RB times RC, the sum of the 3 resistors, gives us 63.6 ohms. And the sum for the conversion for R3, RA and RB plus the sum of the 3 gives us 140 ohms. So it's a pretty simple conversion. So that's the conversion from a delta to a Y. And so when we're done, you just redraw the circuit, 25 ohm, 63.6, 140 ohms. Going the other way, to convert a Y to a delta, so now we've got a 1K ohm, a 2.2K ohm, and a 5.6K ohm. So the relationships the other way are RA is equal to the product, the sum of the products, R1, R2, R1, R3, R2, R3, and we divide by R2. And so when we run those values through here, run them through your calculator, you get 9.15 k ohms. Okay, we do the same thing for RB. RB becomes, again, that sum of the products, but this time we divide by R1, and we get 20.1 k ohms. And for RC, again, the sum of the products divided by R3, we get 3.59 k ohms. And so the conversion then looks like this, back to a delta, where we have RA, RB, and RC with the values that we just solved for. Okay, so like I said, it's not difficult. The going from Y to delta has a few more steps in the math, but nothing difficult to do. Okay, and looking at a specific example here where we're going to convert a bridge circuit to a series parallel configuration, you can see what they tell you to do. Identify RB, RA, and RC accordingly, and forms a delta. R1, R2, and R3 then form the equivalent Y for this circuit, and then we can redraw the relationship in a series parallel. So it's just a way you can see of using those tools to make a simplification in the circuit. It has a few steps that you have to do, but it certainly makes the math a lot easier. So in this example, you can see they've asked us to do the same thing. RA, RB, and RC, we do the same steps that we did previously for a delta to a Y. R1 becomes 1.73, R2 becomes 2.12, and R3 becomes 259. So 173K, 212K, 259. So the resulting equivalent series parallel circuit then is shown in the diagram 867. Okay, and what we're going to do is determine the total resistance and the branch current. So that is our our resulting circuit there. So we're going to determine our total as a product and product sum relationship plus R3. So if we look at this, if we go forward, you can see R3 is the series. The two series in parallel relationships then become these other values, okay? So we end up with a value of 3.37 k ohms then for the total resistance of this redrawn and recalculated diagram. To determine the current then, the voltage from A to B divided by the total resistance, 12 volts, so A to B is our source. 12 volts, 3.37 k ohms gives us 3.56 milliamps. Okay, so there's our circuit. The total resistance of the parallel part of the circuit then, our total, they identify our total sub P, 311 k ohms, so that we can determine the current then A to C, the current A to D, and that just becomes our current divider, okay? So we've got all of our resistors that we are calling our total for the parallel. So our total parallel divided by 1 plus RD times IT. So we get 1.72 milliamps for the current from A to C through this part of the branch, and we get 1.84 milliamps the current through this part of the branch. The voltage then from the terminal C to terminal D, okay, those are the points inside here. VCD then is equal to the current I A to D RE minus I A to C RD, RE and RD. So we're taking the currents for each part of the branches here, and we get a value of 7.18 volts and minus 8.08 volts, or minus 0.9 volts. So that's our voltage C to D. VC to D is the voltage across the load, RC in the bridge circuit shown in 866. The load current through RC then becomes VCD divided by RC, that 9/10 of a volt negative, 18 k ohms. We need to go back. There's our 18 k ohm resistor, RC. So even though in the redrawn circuit it's not there, that's actually what we're calculating. So 18 k ohms into 0.9 gives us minus 50 microamps of current. Okay, we can see an example here of a Wheatstone bridge control and temperature measuring unit. So we would have an amplifier and a relay control for an element, and then out here we would have a thermistor then, and then some adjustment here that we can do to balance the circuit. So a way of using a Wheatstone bridge as a temperature measuring circuit. So in chapter 8, this is what we looked at, packed full of interesting conversions, theorems that we haven't seen before, and conversions for Y to delta.